All right, welcome to class. We are starting Chem 351. It's very good to be with you and see you today. Section 1 is here. This is Monday. I am Professor Andrus. I'll be your instructor, your tour guide, your cheerleader, your mentor, whatever you'd like me to be for this class. Organic chemistry a whole year. Most of you will be going on to Chem 352. And a lot of you on to biochemistry 481 for your major programs. So we use the same book for 352. So the ebook, I'll say a little bit about that. So I'm assuming you've seen the syllabus, and I sent out the instructions for the ebook. And how many have already poked around Learning Suite to see the class site? Okay, good. I'm always a little hesitant there. I hit the publish button and cross my fingers. And yeah, it's been working great the last few years. So let's all hope and pray that Learning Suite keeps working the rest of the semester. That's an important thing. Yeah, so today we'll just do the intro. I'm assuming you've read the instructions for the class and gone through the syllabus and the schedule. They're under course content on Learning Suite, and you can print one out, get a hold of the PDF, and make sure you're familiar with that. I'll hit the highlights today and hopefully convince you why organic chemistry is important and why are you taking a whole year of this class dedicated to just one atom, one element in the periodic table. Why carbon? In fact, that's the big question today. Why carbon? In fact, let's see if anybody can answer that now. There's over 100 different elements in the periodic table, right? Why do we have a whole year dedicated to just one atom? What's up with carbon? Anybody? Why is carbon unique? Four bonds, okay. Some other things can do four bonds, but those four bonds come from what that's fundamental in carbon? Dig a little deeper here, maybe. Anybody? Okay, well, maybe you're onto something there. Four bonds, certainly. Yeah, in the back. Ah, yeah, so person way in the back is saying a lot about orbitals and gaining electrons. Yeah, you're on the right track. You didn't say the magic word. How many electrons are involved in bonding with carbon? It fits into the response here. How many? Four. It's a magic number, right? Because then when you bond, that's two electrons in each bond. So that's the magic octet, right? And that's the magic number, the correct number of bonded electrons that can fit around the nucleus of that size. And that's a quantum mechanical idea. It's a fundamental number in nature, that 8 electrons, or the octet, that has to do with the bonding four bonds and the orbitals and how they arrange there. So definitely on to some. There's a couple more things that we'll talk about here in a second. Maybe you're already thinking about it. But that's the question. There we have a reaction here. We're going from an alkene to an alcohol with water and sulfuric acid. You're going to learn a lot of reactions in this class, okay? We know how to run a lot of reactions in the lab and keep track of a lot of them. There are thousands of different reactions. There are, of course, millions of different compounds we know. You're not going to be able to memorize all of them. You have to rely upon the fundamental properties and principles that come out of general chemistry, and then I'll show you how those, of course, relate to organic chemistry. A couple other things here to hit before we go through the course and all the stuff there. This is a blended course. You should know what that means, and I think we've been good at enforcing it here. This is just section 1 today. This is Monday. So you guys, section 2 who are watching the video come on Wednesday, right? And section 3 comes on Friday. You guys have to watch the videos for Wednesday and Friday, okay? That's what that means. And the COVID protocols, you should be aware of that. And everybody's wearing a mask. That's very good. And we'll be, of course, checking that if you come in without one. They have masks available over in the stock room over in the Nichols building. So yeah, make sure you always have one on, and we'll enforce that. Yeah, the videos already mentioned that. They are YouTube videos, and you'll see URLs for them. I think they're higher quality. They're shot with my iPhone and the AirPods. I've compared the different options we have in the room, and I think this is the best way to do it, okay? But you'll be able to see the videos clearly and everything. But it's not synchronous when you're watching the video, okay? Take notes and ask questions. You guys here today can ask questions, of course, and I'll repeat those questions, try to help people out who are just viewing. But office hours and recitations, and Gannon's one of our TAs here, and Colin's one of our TAs. You'll get to know them very well. They'll be Zooming with you tomorrow for your recitation. And recitation is synchronous. You have to Zoom in at that time, 8 a.m. And the university makes us stay on that schedule. If we pick different times, that would conflict with your guys' scheduling. So we're staying at the time. Okay, you don't come to a room like normal. You just zoom in, and that URL is right there on Learning Suite. Okay, so click on that, and you'll see these guys and help you out. Then later in the afternoon, I think my office hours tomorrow is 1 p.m. Zoom in with me. You'll see me without my mask finally, and ask all the questions you want. The ebook, stay opted in. You'll automatically still see the ebook. If you want to opt out and get the ebook somewhere, or get the textbook somewhere else, that's fine. I'll say some more about that. But yeah, I think we hit all that. So let's go up here, Gannon, and look at the overheads and see the cursor should be showing up. Can't use the laser pointer now. That doesn't show up on the video. But there's all the basic info. You can see there, yeah. The book is the 5th edition. Now, if you use an older edition, that's okay. If you opt out, you don't want to pay the 120 bucks, whatever it is. Opt out, get it somewhere else. You can buy the textbook for like $300. A new one, that's about what the price is. But we've negotiated with McGraw-Hill to get you a very good deal with the ebook. And you get the solution manual. And you have the option to go over to the bookstore and have them print out a loose leaf hard copy for you. I think it's another $30 if you do that. So there's a lot of good options there. If you use an older version, though, you've got to get a hold of the 5th edition version to do the assigned homework problems, okay? So yes, we do have homework. Sorry about that. That's designed to keep you on task and to make sure you're focused regularly on the material and working those problems. Yeah, you can see the solution manual right away and just look at it and write it down. Don't do that. We need to see your work. How did you reason through the problems? You do it by hand and then snap a picture of it or scan it in and then upload that document as a single file to Learning Suite. Most people have been submitting things electronically. It's been working okay. If you're not familiar with that, we can help you out with that, or ask one of your colleagues in the class and we can help you with that. But yeah, there they are. One for each chapter. I think we dropped 2 of them. And so, oh, no HEIC files. Anybody know what type of files those are? Any computer guys out there? Those are iPhone files. Those need to be converted. Learning Suite doesn't recognize those files, so convert it. If you have a smartphone, an iPhone, a Mac iPhone, you need to convert that file from your image picture to a PDF or a GIF or a TIFF or whatever. Most of the other standard files Learning Suite can see, but we can't see that. So you'll get a 0 on your homework at first if we can't see it. So, and we'll tell you in the dialog window there in Learning Suite, hey, wrong file type. Make sure you get the right file type. Okay, homework book challenge. Yeah, more homework. No, this one's not graded. It's only turned in at the end. And this is a neat workbook that you create throughout the whole semester that has your solutions to all of the even problems at the end of the chapters, all 15 chapters. It's my way to get you to do more homework problems. Okay, there's a connection between how well students do in this class and how many problems they actually do. Okay, there's an important connection between the hand and the brain. You need to engage with this material, take good notes, structure, reactivity, and mechanism. All starts with your pen or pencil scratching across the paper. And that will help your brain see those patterns and make those connections. Athletes and musicians know this very well. You need to make a connection, okay, physically with the material. We got the main 3 types of molecules, alkynes, alkenes, alkanes up here. Okay, so structure is where we'll start out with. Keep track of that. And doing as many homework problems as you can will help you out. Quizzes, let's see, quiz 1 is already on Learning Suite. Anybody seen quiz 1 already? There's a file there, quizzes under content, and we handle these now electronically. You have to print this out, and please use the actual PDF of the quiz that we have there. Do it by hand, enter your answers, and it's open to everybody. You can get help from me, the TAs, the internet, whatever, okay? Fill it out, and then snap a picture of it, and then upload it to Learning Suite by midnight. Our deadline time-wise is always 11:59 p.m. Don't push it to right at midnight. Depending on how good your clock is or whatever, you may get bounced out. So do it ahead of time there. Okay, exams, yeah, 4 midterms and the final were 200 points. Testing center, we're planning on the testing center so far for tests 1 through 3. After Thanksgiving, we're all online, so that will be test 4 and the final online. And those will be multiple choice, complete multiple choice exams, okay? Worksheets are posted that have harder problems that correspond to each chapter. That's just for your own use. Those are actually problems we've had on older tests, and it gives you an idea of some of the harder problems, okay? Most of the problems on exams are single concept questions, okay? If you know the concept and can, pick the right product or give the right name or a little part of the mechanism, you'll get full credit for it. Some problems, though, require multiple concepts that you have to bring together and figure out, okay? Here's the homework problems. They're in numerous places, both on the syllabus and the schedule. These come from the end of the chapters, okay? And those are the specific problems you need to work, and do that on a piece of paper and snap your picture and upload it by that date. You'll see the schedule here in a second. They're also listed in a couple spots there. Yeah, there we go. 15 of them. Here's the total grading there, the grade cutoffs, the total points. This is approximate. It depends on how well you guys do. You guys create the curve. I just look for natural breaks in the points. I don't use hard and fast cutoffs for grades. You guys bunch together, and then there'll be a break in the total points at the end when I plot it all out. It makes grading easier and more fair, I think. I've got to do a little more work, though. I've got to look through all the points and see where the natural breaks are. But if you're in one of those break areas where there aren't many people, and I see your homework book challenge that's done, I'll give you the next grade up if it's within 3 to 5 points. Okay, is that a fair thing? You guys create the curve, okay? These will probably be pushed down a little bit, okay? So depending on how well you do, like I said, these are just approximate cutoffs right now. But it gives you an idea of how it goes, I think, okay? Yeah, everything's on Learning Suite, display case. It's not downstairs. I think it'll be right here in the hallway. Yeah, and when we hand back test 1, you'll see that, okay? We don't hand back the quizzes. We'll just grade your work electronically right there. You'll have to look at the posted key then to see where you missed problems, okay? If there's any discrepancies, though, on graded work, you need to submit to me a regrade request within 1 week. That has specifics to it. What did we misgrade, and how does your work compare to the key, and where should you get points back, okay? So be very specific and direct for that. And that's submitted to me, just an email with those specifics for that. Okay, yeah, I think we hit most of this already. COVID stuff, videos, unassigned day. Any questions on anything so far? Okay, I know it's 8 in the morning, but you guys look like you're awake, so yes, please.
You mentioned that we want to submit the homework problems on like a single sheet. Can we tackle that? What if they're like really long problems that are not?
Right, question on submitting homework. Do we get it on one sheet? One document, one image. You can lay out multiple sheets and take one image of it, okay? So you gotta get a little good at that. Or you can scan it in as one document too. Different scanners will let you do that. As long as we can see it clearly, that's the main thing. Try to limit the number of files you have to submit though. You can have multiple pages in one file, okay? And we can help you out with that too. But yeah, you'll see my keys. The TAs will have my keys. You'll see how I work the problems, and I have them all on one page, right? Yeah, Gannon and Colin have the keys right now for the homework. And like I said, work ahead, and the first one isn't due till next week, but that's a good thing to be worried about now. Okay, there's the schedule. Yeah, a lot of stuff. It's very detailed. You've probably already seen it. All the topics here are listed right there, the dates, the reading. So chapters 1 through 15. And here's the due dates. Quiz 1 is due next Tuesday. That's what the T means there, the 8th of September. So that's kind of linked to the date over here. And here on the schedule, it's so crammed. I'm just doing Monday, Wednesday, Friday normally. But the quizzes are often due on Tuesday, so you have time to be with the TAs in recitation. and office hours. Okay, so that'll kind of help you out. Yes. The quiz is already available. So a question on the quiz availability, it's already posted on Learning Suite. So you need to turn it in, do your work and turn it in by next Tuesday for quiz one. Okay, you'll see that. Okay, and then you see there exam one. Yeah, so we'll do, basic structures, acid-base stuff, functional groups, alkanes. So a lot of this is right out of Gen Chem. But I'll, of course, be using examples from OChem now. We'll be focusing on organic molecules. Test one, testing center. Yeah, we're planning on that Monday through Tuesday. Tuesday is considered the last day, so the late fee will kick in, I think, at 3 in the afternoon. I don't get any of that money. We've tried to push back against these late fees. We've already nickeled and dimed you guys to death here on fees, but they insist on it. So try to get in there on Monday or early on Tuesday. Okay. So those are the dates. And we're a little bit crammed in the testing center. They're at a third capacity right now. So luckily I got my request in there soon enough to get you guys into the testing center. Now, whether you like that or not, I'm sorry. But yeah, the testing center will be operating under COVID protocols. So get in line early, and take care of your schedule there. I'll say more about that as we get closer, of course. Then we get into other topics, of course, stereochemistry, reactions. There we go. Alkyl halides, a lot of reactions here. Alcohols, you see an alcohol forming reaction right there. Alkenes, alkynes, we've got models of that right there. Oxidations. Oh, and then we get into spectroscopy, mass spectrometry, MS. NMR, nuclear magnetic resonance spectroscopy. And then one final chapter on reactivity, radicals. And that'll be the end right there. There's the homework assigned problems again with a little more info on that. And there's the homework book challenge right there and certified on the final. Okay. So be doing all of the even problems at the end of each chapter. That's a great way to prepare for exams too, working as many problems as you can. Okay, here's why you're here today, right? How to succeed. You all want an A, and I'll give all of you A's if you're all up there score-wise. Okay. In fact, that's my goal as an instructor. I've been teaching for over 20 years now. Hard to believe. Yeah, my hair went white about 20 years ago after I started teaching. No, my hair went white when I was a scoutmaster. Sorry about that. You guys know what that means now. Yeah, they did away with scouting for a reason. There were too many premature white-haired guys in the church. Yeah, no. Okay. Okay. No, here I am playing around with a copier. That's how a lot of you feel entering OChem class, right? And the biblical reference here is it's easier to get a camel through the eye of a needle than it is to get an A in OChem. Is that what it says in the New Testament? I think that's what it says. No, okay. Here's what you need to do, right? You guys are well along in your studies to know how to study for harder classes, right? And this is considered a harder class. We're in class 3 hours a week, and the recommended study time in our department for that is 3 to 4 hours outside of class studying for every hour spent in lecture. So you need 3 or 4 hours. And talk to the people getting A's, and that's what they're putting in. And you know that from classes you've done well in, right? That are harder. You need to do that. You're not getting an A easily in multidimensional calculus or an upper division physics class, right? By just glancing through the book once in a while. So you need to do this stuff. And I'm not telling you got to do all that stuff, but those are the things people do that get A's in chemistry classes, okay? So do some of these things. Studying in a group. Now, when we were normally in person, it was easier to get you guys together in study groups. I've activated the dialogue box so you can see other people in the class. And when you zoom into recitation or office hours, you can see other people in the class too, or people already in the class. Get together regularly and study, especially some of the harder problems, and help each other out on quizzes. That's a great way to do it. And don't worry about, not getting it right at first. Discuss the principles and how you proceed through the harder problems. That's really the key thing there. But yeah, flashcards and outlines. You'll see my chapter outlines for each chapter. you can take that as your starting point and elaborate that and make your own more detailed chapter outline, okay, with all the reactions and structures you need to know, and that will help you, lock it into your mind a little better. So that's good advice, I think. There. Anyway, okay, so why OChem? So for your major program or your pre-professional thing, you're required to take a year of OChem. Why? Why carbon? That fits into that, right? That's a fundamental question. But why are you here? That's probably a more important question, right? And I appreciate it. You guys look great today. 8 a.m. Here you are, eager to study OChem. But why? Okay, why is organic chemistry considered such a fundamental central science topic? Required not only by the MCAT and the DAT, but all sorts of other engineering things and biomaterials and biology and biochemistry, certainly. All the organic compounds in biochemistry, metabolism, DNA, RNA, everything, are all organic compounds. The fundamentals we're learning in this class apply up the line. But I break it out into 3 areas. Important to develop new products. Yeah, all the things we enjoy in modern society, most of them are based on organic chemistry. The fibers in your clothes, stuff in your food, the fuel, all the materials in your house and buildings, everything, how nature works, the biosphere, everything alive on Earth. You can't get much more universal and fundamental than that, I think. Okay, so yeah, satisfy curiosity. Scientists, we want to know how things work. So this reaction written on the board right here, you can say an alkene to an alcohol, but how does it work? That's the mechanism. Organic chemists are eager to know that kind of stuff. And why? Because then we can make variations. We can improve the process or do it with other types of starting materials. And we can make new materials, right? So there's a lot of questions we can answer once we know, okay, and clean up messes, prevent messes. Yeah, that's kind of a political public thing, but that's also an important thing of OChem, I think. All science is a matter of size. We'll be looking at the very small here. I like this because, the physicists have the really large and the really small here. Chemists have the in-between size domain. I like to point this out because of the profound interaction of small molecules. This is Taxol, a very important anti-cancer drug. It has a profound effect, 9, 10 orders of magnitude up the line here. If you have cancer and take this small molecule here, it's highly likely that you'll be cured of that condition. Well, that's a super small molecule. How's it working, right? And then you can see here, electrical forces are the dominant thing here. And it's already mentioned orbitals and electrons, and that's the main thing we'll be looking at, okay? Not conducting materials. We won't be looking at metals per se. Well, we'll have cations now and then. But here we're talking about insulated materials where the electrons are spin paired in a bonding orbital, okay? We're not conducting electricity, but we're affecting bonding and structure and reactivity. These are electrical forces in this size domain. And then super small, we have nuclear forces, right? How do you hold all those positively charged protons inside of a nucleus? They all repel each other, right? Well, that's a tremendous amount of energy that can be released upon fusion of a nucleus, right? Or fission of a nucleus, right? Bring them together, that's fusion, okay? Both releasing a tremendous amount of energy. But we have neutrons also in the nucleus that are neutral, and those are kind of the subatomic glue that holds those particles together. And what are these yellow guys here whirring around this nucleus? Those are the electrons, right? We're not getting into subatomic particles, that's physics. But we'll relate that at least to the 3, protons, neutrons, electrons. You'll be very familiar with those, okay? Why carbon? Well, we got to this a little bit. Incorrect, 4 bonds, extra credit, and electrons there. The other atoms in the second row there, you see boron only has 3 valence electrons, oxygen going across, I guess we skipped nitrogen. No, there it is, 5 valence electrons. And then hydrogen, 1 valence electron. That's in the first row up there. But the valency is a different thing, how many bonds they form. Carbon with 4 valence electrons forms 4 bonds. That's the octet, right? Whereas oxygen has, 6 valence electrons. And that's the unfilled row, right? We don't worry about the core electrons. So that means just 2 bonds here shared and then 2 lone pairs. There's the 8 electrons. So for bonding and the arrangement of the atoms, you have to get to the octet rule, okay? That's the stable form. That's the magic number of electrons you can fit around a nucleus that size. Nucleus is positively charged. It's balanced with the electrons that are surrounding it. It's that balance that has to do with structure and reactivity, right? They have a nitrogen 5. Well, that's 3 bonds and then 1 lone pair, okay? And then 1 hydrogen. That's pretty boring, hydrogen. And then carbon, here's the diversity of the bonding patterns, which are amazing, and we'll get into. Alkanes have sp3 hybridization. We mix all those orbitals at that level and make 4 equivalent sp3 orbitals, and they all point at the corners of a regular tetrahedron. Okay, that's one of Plato's ideal solids. The ancient Greeks thought about this. What does matter look like on really small scale? And Plato said, well, it's all these regular polygons and solid shapes, you know. And he was right about carbon. He thought about the tetrahedron. Well, no, I didn't know anything about carbon reactivity and bonding, but it was one of his shapes that he had in mind. That's a 3-dimensional object. Carbon can also bond with a double bond to one thing and then 2 other bonds. Well, that's 3 total things bonded to. So they spread out in a plane to minimize the electron repulsion. And that's what? Trigonal planar structure. That's a 2-dimensional structure, okay? So carbon's diverse that way. And then if you have a triple bond, an alkyne there, you got a 1-dimensional linear thing, right? That's digonal geometry. You just bonded to 2 things there, triply bonded to 1 over here, whatever it is, and then 1 over here. Well, that's 2 things bonded to. And so to get the electrons as far away from each other as possible, that's what? A linear arrangement, 180 degrees. So it's like Tinker Toys, right? You guys were kids not too long ago, snapping things together in different patterns. That's why we have kids play with toys, by the way. So they'll become organic chemists later on. Well, there's the arrangements. And molecules are just combinations of those things. 1-dimensional, 2-dimensional, 3-dimensional. But you need to look at it in terms of the orbitals, okay? sp hybridization, sp2. Well, where's the other p atomic orbital? There's 3 p's, right? Well, 1 here is in a pi bond now, okay? So these are the ones that are forming the sigma bonds, actually. And we'll need to get into that, sigma and pi bonding. Hopefully you learned a little bit about that in Gen Chem. But pi bonding, sigma bonding will come back to help us out in OChem. So carbon, yeah, can form long chains here, extended things, alkanes. Hydrocarbons can form rings, cyclohexane. We'll look into the geometry and the structure of cyclohexane. It's this puckered chair thing. A lot of functional groups, alkenes, I've already mentioned those, carbonyls, ketones, aldehydes, esters, amides. A lot of carbonyl compounds. And here's penicillin. Here's a drug probably a lot of you have taken, unless you're allergic to it. Combination of functional groups. There's an amide there, a sulfide, and a carboxylic acid. And you see the different bonding patterns. And these stick figure drawings, these skeletal figures, these are the ones we use now in OChem. Every corner is a carbon. We don't draw all the hydrogens. That's kind of boring and repetitive. But this carbon right here, where you see my cursor, is bonded to that carbon and that carbon. And there's how many hydrogens there then? 2, okay? And that's an sp3 hybridized carbon. So that kind of analysis you're really going to get into and see that. This shape, this combination of functional groups leads to the reactivity and the properties of that molecule. So the degree to which you can understand structure and bonding allows you to understand properties, reactivity, and how a lot of things work. Let's see some of those things. Different materials from petroleum, hydrocarbons are cracked thermally, created all sorts of different products here. Not all hydrocarbons come from petroleum. There are renewable sources of that. Polyethylene is just zipping together alkenes, chapter 15. We'll look at those, things like polystyrene, PVC. Cellulose from plants is polyglucose, natural fiber material. And different fuels here, everything from methane on up to isooctane, how your car works. Yeah, you're going to learn how your car pistons work in this class. Conducting materials, everything in your display cases. These are highly conjugated materials. Polyacetylene is an amazing material. It's pliable, but it looks metallic. And yes, it does conduct electrons. It is a conducting material because of the pi bonds all being right next to each other. Polyaniline in display cases and liquid crystals, everything in from your watch to your computer screen to your TV screen now, or organic light emitting diode materials that change their color and their properties in response to very weak electrical fields that they experience. So a lot of things in engineering and electronics are based on organic compound. Dyes and sensors, I already mentioned a couple there. Yeah, I won't say any. Flavors and fragrances, you're probably familiar with some of these. Everything from vanilla, vanillin, caffeine, capsaicin, there's a fun one. Where's that found in nature? And what flavor is it? Peppers, hot peppers, yes, the Scoville scale. How hot is that pepper? Well, it depends on how much capsaicin it has in there. So there's a lot of things here with flavor. Herbicides, pesticides, glyphosate, Roundup, warfarin, DDT. Some of these have been banned. Yeah, some cleanup issues. Chrysanthemic acid from chrysanthemums, limonene. These are natural pesticides that are more commonly used. Drugs. What's the big drug that's talked about today? The anti-COVID drug. Kind of a breakthrough. What's it called? Starts with an R. Anybody heard the name? I didn't put the structure up there, sorry. Remdesivir. Okay, that's the one everybody's talking about. Originally developed for the SARS virus about 15 years ago, but they found in assays that it is active against the coronavirus. If you take it soon enough, you can be cured of that pretty quickly with remdesivir. A lot of it depends on how far the disease has progressed, of course, like cancer, and how quick it's treated. But drugs are developed here, and a lot of you have probably taken some of these, right? Hopefully not all of these. Hopefully not that one, okay? But yeah, okay. Chiral molecules, stereocenters. We'll get into that real quick. This form of asparagine with an S stereocenter tastes bitter. This one tastes sweet. You can see some other examples there. Molecules of life, I mentioned biochem. Here they are. There's 4 classes in life. Amino acids and proteins, there they are. Lipids and fats, lipid bilayer membrane. Carbs, carbohydrates, starch. A lot of things we could talk about there. Glycogen, this is blood sugar, glucose. DNA, which is deoxyribonucleic acid, right? There's the deoxyribose right in the middle, the phosphate, and then the base pairs, and then the double helix. All the genetic material. Molecular genealogy, okay, it's all done through DNA sequences, right? Everybody's unique. Yeah, we'll learn a lot about, mainly in 352. So I'm kind of reviewing what you're going to see in 352, the amino acids. Conformations of protein, steroids, yeah. Hormones, vision, there you go. Alkenes, polyalkenes. This is more than 351. We'll see this with Z and E alkenes. Here's the vision. The photon harvesting molecule in the back of your eyeball and the retina. There's 3 different types of the protein that harvest the light at those different wavelengths. Yes, all these sensory processes in the body are all based on OChem too. Sorry, it's everywhere, right? And it's this conformational change from the cis double bond to the trans double bond that then impinges on the optical nerve, this conformational change that's affected there. We know a lot about how the photon of different wavelengths are harvested, the science behind light and the different images that we see there. But we know nothing about how the brain processes those impulses and you create the image you actually see in your mind. So there's your philosophical idea for today. What are you actually seeing in your mind? Are you actually seeing the physical object? No, you're seeing the light emitted from those objects. Your brain's then interpreting that, right? You can't get more amazing than that, I don't think. If you want to win a Nobel Prize, figure out how the brain creates that image, okay? But we know the initial steps here, but not the rest of it from the actual image. Synthesis, yeah, we make a lot of molecules. This is what I do. I'm an organic chemist. We set up reactions, we run things, we monitor them. We don't do super large scale like this. We do small scale stuff like this. But we do a lot of purification and then NMR and figure out how things are. Yes, we have these big NMR machines. They're like MRI machines in the hospitals. These are multi-million-dollar devices. Superconducting metallic coils create these high electrical fields, high magnetic fields, and you'll learn about NMR later on. But that's how we carbon structure. We have to pay homage to these old guys, these old dead white guys. Sorry about that. They did a lot of good things. Wohler was the first guy to make a natural product synthetically. He made naturally occurring urea without the aid of a dog or a bladder. This is out of urine, right? But before that, everybody thought only nature could make naturally occurring organic molecules. It's the vitalist theory. But no, we know how to make any organic structure we want to now with synthesis. Colby soon after made acetic acid, which is the essence of vinegar. And then William Perkin, I like to point him out, not just because he looks like Joseph Smith, but because he was a young guy in the 1800s and he had an idea, he had a vision. He wanted to make this drug that was known at the time called quinine. And there was enough known about quinine. By the way, what does quinine treat? I think you can know that. It's still used to treat this disease, by the way, over 100 years later. Malaria, okay? Quinine treats malaria. And he knew it was this formula, and he knew another molecule that had half that molecular formula. Didn't know anything about the structure, but he knew about the ratio of atoms, the molecular formula. So he said, well, I'll try to double allyl toluidine here and get this structure. He didn't get that. He got mauve, which is a purple, intensely purple color, and he spilled it on his lab coat and made a real mess. And even though he didn't make quinine, he looked at his lab coat and he tried to wash his lab coat. And guess what? That purple stain didn't come off. And hence the dye industry was launched. And we made all sorts of colored materials over 100 years ago. And then they started staining different microorganisms. And they noticed some of the dyes, some of the colored materials killed some cells selectively, could kill bacteria and viruses selectively. And so hence the drug industry was born. It all came out of this naive but highly motivated young man, William Perkin, 16 years old at the time, started working on this, but launched a couple different industries, dyes and drugs. Can't beat that. And Michael Sweat with silica gel chromatography allows us to purify things. So here's a modern drug here. E.J. Corey at Harvard making Tamiflu, also Tamivir. Some of you maybe have taken that. It's been around now a while, but this is one of the more recent drugs that was completely designed using rational drug design. It wasn't based on a natural product. It was based on a known receptor here on the virus, which needs to do its action to allow the virons to fuse with host cells and complete the infection process. So this drug was designed to inhibit that fusion of the virus with the host cell. And it's very effective. If you get the flu within 48 hours and start taking Tamiflu, it's 85 to 90% of people will be cured of that condition. But it takes 12 steps to make. It's kind of an expensive drug, but there it is. Yeah, and I'll show you some other examples, get into more of the details. 352 will do glycolysis. We'll also do citric acid cycle, cell metabolism. OChem, there's a little summary of some of the highlights I've already mentioned. Some biochem, yeah, there's the things there. Analytical chemistry, yeah, we will get into some analytical stuff, like I said, with mass spec and NMR, which is related to MRI here. And separations are also important in analytical stuff. Okay, so yeah, blah, 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 OChem. I could go on forever. I'll stop now. What do you need to know taking this class? So you probably still feel like that guy at the copier in red, screaming, wondering how you can get an A in this class. That's how you guys look today. You look sharp, right? You're prepared, dressed for success, ready to go. And you'll still look that way if you go throughout the semester doing this stuff, right? Doing the stuff you know. If you don't do that stuff and don't put in the time, guess what you're going to look like? You're going to look like that. And that's a picture of me at the end of every semester right there. So don't look like me. I look like that today kind of too. I don't know. My hair's not sticking up completely there, and I've shaved this morning, so I don't look completely. But yeah, you're going to look like this and feel like this. And not only because you're not understanding the material, but you're not getting a good grade if you're not doing this stuff in a dedicated way. So I'm trying to be realistic with you, and hopefully you've got a plan to do that. Here's another sharp looking student. This is actually a basketball player from years ago who was in the class. We snapped a picture of him. He got an A in the class because he had OChem on the brain. So it's a big section of his brain dedicated to OChem. And what are the issues of OChem? How do you have success in OChem? Well, I've been mentioning them. There's three, and I'll harp on this repetitively. You'll hear this over and over. Number one, structure, bonding. Okay, 4 bonds to carbon, 4 valence electrons, sp3, sp2, sp, hybridization. That's the big topic here in chapter 1, okay, how those things come together. Those fundamental structures, though, say a lot about the properties, how polar the molecule is, whether it will dissolve in water or not, whether it will react with different things, what shape will it have, how volatile will it be, what's its boiling point, melting point. You'll have a feel for that if you understand structure, okay? That's the first level of understanding. What's the next thing here? Reactivity. So A plus B going to C. And you've got it up here, right? I'll go back to the board here in a second. We still have a couple minutes. Reactivity. So knowing the reactions. There'll be new reactions for every chapter, and they'll come fast and furious, especially in the second and third sections of this class. We'll get into alkene reactivity, alcohol reactivity, alkyne reactivity, and then radical reactivity, okay? And that can be overwhelming, a lot of reactions to keep track of. Don't memorize them all. You can't do that. You need to apply the principles. And based on those principles of understanding the structure, that's how you're going to know how things react, okay? What's the next thing? So we got structure, reactivity. What's the third? Anybody? I said it before, I think. Starts with an M, and I'll do it on the board here in a second. What is it? Mechanism, that's right. Okay, so the details of the flow of electrons. Here's a filled orbital, it happens to be a lone pair, and I'm drawing what? A double-headed arrow. I'm showing the flow of the electrons. We always draw the arrows from where the electrons start to where they end up. This is an empty orbital here. And by the way, that's how all reactions work. Filled orbital goes into an empty orbital. There's really only one mechanism in OChem. I joke about that, and people don't believe me at first, but you'll see when we do mechanisms, where's the empty orbital? Where's the pair of electrons? Where's the nucleophile? Where's the electrophile? And you'll see how the flow of electrons work. It's identifying what the nucleophile is and what the electrophile is that can be tricky, right? But Gannon's figured this out, Collins figured this out, and that's the basis of OChem, okay? Where are the electrons and where are they going? And if you keep track of that, you'll be just fine. So let's see, back to the board here, chapter 1. We can start a little bit on chapter 1 here. I've already got something on the board to see that. Here's my outline, periodic table, ionic bonding, covalent bonding. So here's all the topics in the different sections. So like I said, I'll show you an outline for each one. And today, you know, we're on the computer overhead a lot, but most days I'll be at the chalkboard, okay? You need to follow along with me, take notes. I see a lot of pens out, that's good. You guys are writing stuff down. Here's the stuff and the details we'll go into, right? And you see octet rule, Lewis dot structures. A lot of this looks familiar, okay, from Gen Chem. Some of it will be very familiar. Other things you'll need to brush up on, but here's the main thing with OChem, ethane. That's an alkane, sp3 hybridization, saturated bonding, okay? Maximum amount of hydrogen. Here's 2 hydrogens removed to make an alkene. That's sp2 hybridization with a pi bond and a sigma bond. There's 4 electrons shared here. Every line in OChem means 2 electrons, right? Every corner means a carbon, and we don't always add all the rest of the hydrogen in. We always show all the heteroatoms, all the non-carbon atoms, like nitrogen, oxygen, boron, phosphorus, whatever. You'll see those. But normally we'll just have stick figures with carbon at the corners or at the end, and then you need to get good at adding in the rest of the hydrogen. And there's alkyne, the triple bond guy. The bonding, we'll talk about the generalities of how they work, of course. The molecular orbitals, I'll show you those. We'll go a little bit beyond the book that way. Electronegativity. It's the other thing about carbon. Why carbon? 4 valence electrons, 4 bonds. What about electronegativity? Is that unique for carbon? Anybody? What do we mean by electronegativity? Yeah, it's the propensity of an atom to polarize electrons toward it. Depends on how close it is to the right side of the periodic table, how close it is to filling that octet. If it's very close to the right side, it's highly electronegative. The most electronegative atoms are the halides, right? Fluorine's the most electronegative. But look, oxygen's close too. It's very electronegative. Nitrogen, not so much. And then carbon, where is it in the periodic table relative to the others, really? It's right in the middle. It has modest electronegativity, which is good for bonding, right? You don't want anything too extreme. Because if you're very electropositive, very low electronegativity, you're a metal. You're giving up all those electrons right away. You're not hanging on to them. If you're a halide, you're pulling those electrons in. Carbon wants to share its electrons. It's the most magnanimous atom, you can say. It wants to share those electrons and spread the joy and spread the bonding evenly. And that tends to make more stable molecules. Yeah, so we'll get into that there. But atomic orbitals, yeah, we'll leave it right there. Let's go back to the board here for a second and see what we need to do there. So let's see, getting into the topic. So core principles, yeah. So carbon, when we talk about carbon, what is it, right? It's one of the atoms there. And how are atoms constructed? Well, there's these protons and neutrons in the nucleus, right? And protons are positively charged, and that's where all the mass is. 1 atomic mass unit per heavy particle, right? 1 gram per mole. Depends on how many are in there in the nucleus. And then what? The electrons are the smaller particles that are found outside that nucleus, okay? This is where all the mass is, the dense interior of that. So when we look at carbon, what is it? Well, it's element number 6. That's usually written as a subscript there. And that's just the progression of the periodic table. We get to element number 6 there. What does that mean, though? The 6 means what? There are 6, the number of what? Protons, okay? But let's look at the mass of carbon up there. 12 point, what? 011. What does that mean in the periodic table? And how does that relate to the 6 in carbon? What is that?
Usually has about 6 neutrons.
What's that?
Usually has about 6 neutrons.
6 neutrons. How did you get to that? Somebody says that means it has 6 neutrons. How did he know that? Yeah, the atomic mass. So each one of these is 1 atomic mass unit. So if it's carbon 12 there, and this superscript has to do with what? The number of neutrons. So that means what? There's the number of protons plus neutrons. So for carbon to be a 12 here, the 6 here is linked to what atom it is, okay? As the number of protons goes up, that changes the type of atom it is. But the neutrons can vary, okay? Carbon 12 means there's 6 there. But look, the atomic mass in the periodic table is 12.011. So what's up with that? Isomers, or you're right saying an I word, isotopes. So there's some C13 in there, which is the heavy isotope. So how many protons? 6. And how many neutrons then? 7. And you've probably heard about this one too, carbon 14, okay? Which is the radioactive one. You can do radiocarbon dating there. It decays with a half-life of about 5,000 years. You can estimate how old organic materials are. So there's a lot of neat science that goes there. But that's very rare. And this means what? It's like 1.1% carbon 13 and a very, very tiny amount of carbon 14. A lot more we could say there. But these have to do with isotopes, right? And these isotopes have different numbers of neutrons we're looking at there. And we'll see that concept later on as we look at a couple things here. Oh, hydrogen. Let's back up to the simplest one. And that just means what? 1 proton. And often we'll call hydrogen just the proton. But we also have deuterium, which is hydrogen with 2 there. And we also have tritium, hydrogen with 3 there. Okay. And we've got to leave it there. be thinking about this mechanism. We'll start right here next time. But we'll see you guys next Monday. No, next Monday will be a holiday. You guys will have to watch the videos on Wednesday and Friday, okay? On Wednesday, we'll see section 2 in class. Okay, so very good. We'll see you next time.